I discuss in this video the so-called representation theorem for finite Boolean algebras. Finite Boolean algebras. And I will go through a number of steps to get to this result, but I want to tell you right from the beginning what this theorem is. In some sense, it's a surprising result that I hope you will appreciate from the point of view of its mathematical beauty. So what the result is that I'm going to eventually prove after I set up some foundations is that really any, so this is what we will prove, any finite Boolean algebra is isomorphic, and I will define what this means, to some power set Boolean algebra for some set X. So this is a very interesting result, and perhaps not quite intuitive that it should be like that. So as a consequence, we also have that any finite algebra Boolean algebra has cardinality, meaning has a number of elements equal to 2 to the power n for some n. And so we will get to this. There are a few initial results that I want to, a couple of initial results I want to prove, and then I introduce the notion of isomorphism for Boolean algebras, and then we are going to establish this result. And it's going to be a constructive result for a finite Boolean algebra. We are going to construct such a set X such that the power set of X is isomorphic to your Boolean algebra. But first I want to prove some results that in fact hold in general for Boolean algebras. To prove them, I need first the concept of an atom. So what an atom is in a Boolean algebra. So if I have a Boolean algebra and Boolean algebra, and I also have the partial order relationship that we discussed about in the previous lecture, define all this Boolean algebra in the usual way, then we will say that element X in B, so the Boolean algebra, let's denote this by B. So X in B is called an atom if first of all X has to be different than 0, and then second, if we have an element between 0 and X, then Y is X. So in other words, what an atom is a non-zero element of your Boolean algebra such that there is no other element between 0 and X. And when I say between, I mean in the sense of this partial order we have defined in the previous lecture on Boolean algebras. So an atom is in some sort of minimal non-zero element of your Boolean algebra. There is no other element between 0 and that element. And with this concept, I'm ready to formulate these two general results I want to prove before we can talk about the representation theorem. So these are the two results. They are Lemmas 2.17 and 2.18 in your lecture notes. I first formulate Lemma 2.17. And I say I have a Boolean algebra B, and I also have two elements in B. And here is the first property. that this lemma proposes, and that's that b is smaller than or equal to a bar if and only if b times a is equal to 0. The second property is that if a plus b equals to 1, then a bar is smaller than or equal to b. And also by symmetry, we will get this automatically, but I formulate it here. And also b bar is smaller than or equal to a. And the third property is if a times b is equal to 0, then a is smaller than or equal to b bar. And also by symmetry, we get that b is smaller than or equal to a bar. And so to prove this, we focus first on the first property, and we have, so b is smaller than or equal to a bar, and this is equivalent by definition with b times a bar equals b. And in this case, what we have is if we start calculating b times a. So b times a is going to be, I replace instead of b, I put b times a bar, so it's going to be b times a bar times a. And this is b times a bar times a. This is equal to b times 0, and this is equal to 0. On the other hand, if BA is equal to 0, then B equals B times 1, and this is B times A plus A bar, and this is BA plus BA bar, and this is equal to, because this is 0 based on our assumption, this is equal to BA bar, which implies that B is smaller than or equal to A bar. So that establishes the first property. And in fact, I'm writing here, and I would like to ask you to check for yourselves from the lecture notes that the properties 2 and 3, they follow from the proof of Lemma 2.6 in your lecture notes. On the other hand, I want to formulate now Lemma 2.18. So Lemma 2.18, it says, well, let's have a Boolean algebra. X, an atom. So remember, it's a non-zero element such that there is no other element between 0 and x. And so there are two properties that this lemma establishes, and one is x is smaller than or equal to a bar if and only if x is not smaller than or equal to a. And the second property is if x is smaller than or equal to a plus b, then x is smaller than or equal to a, or x is smaller than or equal to b. And so to prove this, we have the first property. Because x is an atom, And also by your Lemma 2.13, this was the third property I'm using from Lemma 2.13, we have that x times a is smaller than or equal to x. So based on these two facts, we get that x is not smaller than or equal to a if and only if x times a is different than x. And that's really if and only if x times a is equal to 0. And now, based on the lemma that we just proved, lemma 2.17, the first property of that lemma, we get that this is in fact equivalent with x smaller than or equal to Now, for the second property, we have indeed x, by assumption, x is smaller than or equal to a plus b, which really means that, so this is equivalent with x equals x times a plus b. And then if I develop this right-hand side, I'm getting that this is x times a plus x times b. Now, if both xa is 0 and xb is 0, then x would be 0, which is a contradiction because x is an atom. So this is impossible because x is an atom. So either x times a is different than 0 or x times b is different than 0. Now, assuming I have this, then this is going to really imply, again by lemma 2.13, and I'm using the third property, that 0 is smaller than or equal to x times a is smaller than or equal to x. Which really implies, because x is an atom, that x times a has got to be equal to x, and this is equivalent by definition with x smaller than or equal to a. And with exactly the same argument, if it happened that this was the case, then this implies by exactly the same argument as in here that this is in fact x smaller than or equal to b. So all in all, what we prove is that if x is smaller than or equal to a plus b, then indeed we have x smaller than or equal to a, or x smaller than or equal to b, which really proves the second property of this lemma. So with these results, now we are ready to formulate and to prove this representation theorem. And this is going to go in the following way. First, I define the notion of what an isomorphism is. So I have this definition. And let me just take two Boolean algebras. So I take B with the operations plus, dot, bar, some element 0 and some element 1. And I also take another Boolean algebra. Let's say this is set, say B prime. I have a different addition operation. I have a different multiplication operation. I have a different unary operation. I have obviously a different 0 and a different 1 element. And let these be two Boolean algebras. And I say that function F from B to C is called an isomorphism of Boolean algebras if the following conditions are satisfied. So F has got to be a bijection. And then F also maps the addition operation of B into the addition operation of B prime. In other words, F of plus B equals to FA plus F of B for all AB in B. Same is true for the multiplication. A times B is mapped into this multiplication operator of B prime. The same is true for the unary operator. So F of A bar is the unary operator applied to FA. So FA tilde, where tilde is this unary operator on B prime for all A in B. And also the zero element of B is mapped into the zero element of B prime, as well as the one element of B is mapped exactly into the one prime element of B prime. So in other words, what we have is the notion of isomorphism being a bijection between sets. I'm sorry, this was B prime. So it's a bijection between B and B prime in such a way that this bijection is faithful to the structure. So it maps addition into addition, multiplication into multiplication, unary operator into unary operator, and these constants into the corresponding constants of B prime. So with this definition of isomorphism, we are now finally ready to formulate and to prove the main result of this lecture, which is the representation theorem. And as I anticipated, this theorem says any finite Boolean algebra B is isomorphic with some Boolean algebra P of X for some set X, and then obviously for some finite set X. So that's the theorem, and here is how the proof goes. So this is going to be a constructive proof, and if I denote explicitly the structure of this Boolean algebra, so it's a set, the base set B, and I have the addition, multiplication, the unary operator, the 0 and the 1 elements. And so this is a, by hypothesis, this is a finite Boolean algebra. And I'm going to define, so I will say let X be a set of all atoms of B. And what I would like you to observe is that X is definitely non-empty for any Boolean algebra. And the reason for this is that we have anyway that 0 is smaller than or equal to 1, and 1 is a non-zero element. And so if these are the only two elements in your Boolean algebra, then 1 is an atom, and in fact is the only atom in that case. But if there are other elements, they have got to be between 0 and 1. And so those elements are either atoms themselves, or then there are going to be some smaller elements between themselves and 0. And so eventually, if I continue this line of reasoning, I'm going to get that there will be some atoms in my set. So in any case, the set of atoms is non-empty. And this is a set X that we are going to use for our result. In other words, we are going to show that our Boolean algebra is exactly isomorphic with the power set of this particular X, the set of all atoms of B. And so I'm going to define the function that we then show that it's an isomorphism. So the function that we need is a function from set B to the set of all the subsets of X. And this is defined simply like this. If you take an element from B, then you are mapping it, the set of all the atoms, so all X in X, in such a way that X is smaller than or equal to B. So we will show that this is a, so prove, that F is an isomorphism between this Boolean algebra and this Boolean algebra that has union as addition, intersection as multiplication, complement as the unary operator, the empty set as the zero element, and X as the unary element. So we will have to show that the addition on B is mapped well into a union, the multiplication is mapped well into the intersection, and so on. So we will prove these properties one by one. So the first thing that we need to show is that, in fact, the function f that we've defined here is a bijection. So let's focus on that. So I just remind you that, just so that we can follow on this whiteboard, X, set of atoms of this Boolean algebra, and f is defined from B to X. In this way, f of B is exactly all the atoms that are under B. So first observation that we need to show is that f is bijective. So we do that in two steps. So claim f is injective. So to prove injectivity, let B1, B2 be elements of B and two distinct elements of B. And so what I'm saying here, I'm just writing this implication and then I comment on this. It follows that B1 is either not smaller than or equal to B2 or B2 is not smaller than or equal to B1. And in fact, to see that this implication is true, it's actually much easier to see that the reverse implication when we apply the negation on this side. So the negation of this side implies trivially the negation of this side. So it's much easier to see, in fact, the reverse implication on the negations of these properties than it is to see this one, but it holds trivially with this small observation. So either one of these is true, so let me just assume that this is the case. If the other one was the one that holds, then the argument would be completely symmetrical. So assume, for example, that B1 is not smaller than or equal to B2. And so from Lemma, 2.17 that we just had, it implies that B1 times B2 bar is not 0. So since this is not 0, this implies that there has to be an atom. So there is atom X such that X is smaller than or equal to B1 times B2 bar. And so now it follows by Lemma 2.13, and I'm using the third property of that lemma, that when I start to calculate this B1 times B2 bar, this is in fact smaller than B1, and B1 times B2 bar is smaller than or equal to B2 bar. And so from these two, and the fact that X is an atom, what we get is that X is smaller than or equal to B1, X is smaller than or equal to B2. I'm sorry, B2 bar. So from this, it follows by lemma 2.18 that X cannot be smaller than or equal to B2. So this is an element of f of B1 because X is smaller than B1. So X is in f of B1, and X is not, because of this fact, X is not in f of B2. So this implies that f of B1 is different than f of B2. So what we got eventually was we took two elements, B1 different than B2, and we have shown that f of B1 is different than f of B2, which establishes that f is indeed injective. So for subjectivity, so the other claim I want to prove is that f is surjective. And for this to be proved, I'm just going to take a subset of X. So let me just denote this by elements. So let's say we have k elements, x1, x2, xk. So I'm taking such an arbitrary subset of X. And I'm going to take their sum. These are elements of B, so I can make operations on them, and so I'm going to denote their sum, x1 plus x2 plus all the way to xk. I'm going to denote this by B. And so that we are completely formal about this, this sum is going to be obviously defined if I have at least one element, but if I have no elements here, then I'm going to just say in my definition that B is equal to 0 if K is 0. And so we prove that really this element B is mapped by our function exactly into the set x1, x2, xk. So I want to show this, and that's going to completely establish our claim that f is surjective. So if I prove first this part, then if I take any element from this set, so on xi, by lemma 2.13, And I'm using here the fourth property in that lemma. Xi is smaller than the sum of all these elements. And this is true for all xi in here. And this, remember, was equal to b. So that implies that xi is in f of b. Proving the inclusion I wanted to prove. And for the other inclusion, if I take some element in f of b, then by definition, by the way I have defined f, we get that x is an atom and x is smaller than or equal to b. So b, remember, this was x1 plus x2 plus all the way to xk. And now lemma 2.18 implies that there has to be an I, one of these elements, there has to be an I in such a way that really x is smaller than or equal to xi. And remember that x was an atom, so x is definitely non-zero. And since xi is an atom, and from these two, it follows that really we have to have that x is equal to xi, meaning that x belongs to the set x1, x2, xk. And that establishes the other inclusion we wanted to make. So with this, we have managed to show or claim that this is f is indeed surjective. So now, for the rest of the proof, what we need to show is that f is faithful to all the operations of these two Boolean algebras. So what we need to show is that f of 0, if I take the easier ones first, so I have to show that f of 0 is really mapped into the empty set, and f of 1 is mapped into the full set x. And these are indeed true, because x is smaller than or equal to 1 for all atoms x. And another one, if I focus now on the multiplication, we need to show that f of b1 times b2 is equal to f of b1 intersected with f of b2. And for the summation part, we need to show that f of b1 plus b2 is equal to f of b1 union of with f of b2. So b1, b2 is obviously, as we discussed before, smaller than or equal to b1, and also smaller than or equal to b2. And so what this means is that f of b1 times b2 is necessarily included into b1, f of b1, and also is necessarily included into f of b2, meaning that it's also included in the intersection. On the other hand, if we take an element x of the intersection of fb1 and fb2, then by the definition of f, we get that x is smaller than or equal to b1, and also x is smaller than or equal to b2. And then it follows by lemma 2.13, and I'm using the fifth property of that lemma, that x is also smaller than or equal to b1 times b2. And so this implies that x belongs to f of b1 times b2. So the conclusion is that indeed we have established the equality of b1, b2 equals f of b1 intersected f of b2. So if I focus on this side of the proof, remember that we have b1 is smaller than b1 plus b2, and also b2 is smaller than or equal to b1 plus b2. So this implies that really f of b1 is included into f of b1 plus b2, and also f of b2 is included into f of b1 plus b2. And obviously, based on this, the union is included into f of b1 plus b2. On the other hand, if I have an element x in f of b1 plus b2, then by definition x is smaller than or equal to b1 plus b2. Then lemma 2.18 implies that x has got to be smaller than or equal to b1, or x is smaller than or equal to b2, which implies that really x is either in f of b1 or x is in f of b2, which is really implying that x is in their union. So we have also established, in this case, the claim we wanted to have, b1 plus b2 is exactly equal to f of b1 union f of b2. So the only thing left for us to prove is the complement. So to prove the complement, we have to show that f of b bar is exactly equal to f of b complement, which really in our case is x minus f of b. So that's what we need to show. And the point is that by lemma 2.18, we have that for all atoms in X, we have X smaller than or equal to B, if and only if, so if and only if X is not smaller than or equal to B bar. So this can be exactly reformulated to get that f of b bar is x minus f of b, which is exactly the claim that we wanted to establish. So with all these arguments, we get our result proved. And again, the result is impressive, and it says that any finite Boolean algebra has got to be isomorphic to some power set of some finite set. And so I will just show you now how this goes like for a particular example. How do we build this set X? How does it look like in practice? So this is the example. You have it also in the lecture notes. This is the example 2.20 in your lecture notes. And in this example, I'm going to take set A to be all the natural numbers with the property that A is a divisor of 30. So this is a fancy way of saying I'm going to take the set 1, 2, 3, 5, 6, 10, 15, and 30. And I would like to define some operations on this set in such a way that I make it into a Boolean algebra. And the operations I have in mind are going to be, on one hand, I take least common multiple, denoted by LCM. And I'm also going to take the greatest common divisor. And I'm going to write this as GCD. And if we think about these operations, I'm going to somehow anticipate that the least common multiple is going to play the role of our addition. And the greatest common divisor, I'm going to define it to play the role of our multiplication. So if we think like this, then we will have to define the zero element in such a way that really the remember the zero element was having this property that 0 plus a has got to be equal to a for all the a's. So what this means for us is that instead of addition, we have this greatest, so instead of addition, I'm sorry, we have the least common multiple. So the least common multiple between our zero element that we have to identify and any element, this has got to be a. And so what this means is that really this mystery element has to be a divisor of a, or the divisor of a for any a. So if we look at this set, obviously the only element, so the zero element, so this will be 1. 1 is the only divisor of all the elements in this set. And with the same argument, the unary element or the one element, remember this had the property that 1 times a has to be equal to a for any element a. And in our case, because the multiplication in our case is the greatest common divisor, so the greatest common divisor between this mystery element we have to identify and any a has to be a. And so what this means is that really a has to be a divisor of this mystery element for all the a's. And when we look at this set, obviously the only element satisfying this is 30. All the other elements are divisors of 30. So this will be, for our set, this will be 30. And so what's left to define, just so that I make this set into a Boolean algebra, we have to define the unary operation. The complement, if you like, the complement operation. And to define this, remember that there was this property that was uniquely identifying the complement of a number, and that was for any number a, the complement is that unique element that satisfies these two properties, a plus a bar is equal to 1, and a times a bar is equal to 0. So what this means for us is that least common multiple of a and a bar has got to be 30, and greatest common divisor of a and a bar has got to be 1. And we can solve this set of equations for all the elements in this set, and we are coming up then with this idea that there is only one way to define this, and that is for our elements 1, 2, 3, 5, 6, 10, 15, 30. The complement of 1 is 30 and the other way around. The complement of 2 is 15 and the other way around. The complement of 3 is 10, and the complement of 5 is 6. And really, this you can find out by just solving this set of equations for all possible cases of A. So with this operation, we have this set A equipped with the least common multiple as the addition, the greatest common divisor as the multiplication, with the bar element that we have just defined in here, and as a zero element we have number 1, and as the unary element we have 30. We have now all the ingredients we need to think about this as a Boolean algebra. And I make the point that this is a Boolean algebra. This requires a proof. We will have to check all of those 10 properties in the definition of a Boolean algebra. But they follow trivially, simply based on the argument that the least common multiple and the greatest common divisor, they are commutative, they are associative, and they are also distributive to one another. And also, one needs to check, but I will not do it in this example, that indeed also the complement function satisfies all the properties that it should satisfy. But so I'm skipping those arguments and leaving them for you to check by yourselves. It's not difficult to check all of those 10 properties to convince yourselves that this set having 8 elements, and with this addition operator and with this multiplication operator, with this complement operator, and with these two constants, this is indeed a Boolean algebra. So what I would rather focus on is to show you how is this now isomorphic to a power set Boolean algebra. And the reason we have this example here is that it's not intuitively clear what this set X is. So it pays off to now apply the technique that we had in the proof of our representation theorem to build our set X, because intuitively I would argue that it's difficult to see it from the definition of A. And so the idea of the proof was we will define X. So let X be the set of atoms of A. And remember that we had A smaller than or equal to B. This was in general defined as being equivalent to A times B equals A. And in our case, the multiplication is the greatest common divisor. So the greatest common divisor between A and B has got to be A, which is the same way as saying that A has to divide B. And so the order we have in this Boolean algebra of ours is that A is smaller than or equal to B if and only if A is a divisor of B, and the smallest element in this Boolean algebra is 1, and the biggest element of the Boolean algebra is 30. So, in other words, if we think about the set of atoms, these are essentially the prime numbers in this set. So, with this observation, it becomes clear now that our set X has got to be exactly 2, 3, and 5, exactly the prime numbers in set A. Also, when we think about how does function f map an element into a subset of X, remember that f of A was, these are all, by definition, these were all the atoms with the property that X is smaller than or equal to A, and that is, I'm going to just continue here so that I don't have to build a new whiteboard. So, so this is now continued in here. So I get that f of a is equal to x, one of the elements of 2, 3, and 5, with the property that, and remember, x smaller than or equal to a was equivalent with x divides a. So that's what I'm writing here. So it's going to be essentially a is mapped into its prime factors, 1 of 2, 3, and 5. So for example, f of 6 is mapped into its prime factors, 2, 3. For example, f of 15 is mapped into its prime factors, 3 and 5.